course, the primary contact for Element Tempe EMI. And today we're actually kind of talking about our reverb chamber. It's new. I think a lot of you saw our presentation. For anybody who didn't get to see the presentation, we'll be doing it afterwards. But I've been here for about 2 years, and it's been an awesome learning experience. And I'm introducing Eric Borgstrom. He's our senior technical manager for pretty much all of America. And yeah, he's been doing EMI for about 40 years and serves on the DO-160 committee. Been doing that for about 30 years. And he's going to talk about our reverb chamber today. So I know a lot of you had questions that I wasn't able to answer, but he'll definitely be able to answer these questions. So thank you.
Thank you all for being here. Thank you for inviting me. I appreciate that. I'll start out by saying that it seems like these presentations like this always happen after lunch. And so everybody's tired a little bit, maybe. You know, we had a really great lunch here. And I hope, don't forget the cookies. You got to have those Oreo cookies that look like, that are Element branded. Those are great. So I'll say, I don't mind if you fall asleep. But if you start to snore, you'll probably get a cookie thrown at you. So you've been warned. Okay, so, sorry, I get my magic wand. All right. So as Brandon said, we'll be talking about reverberation chambers. And I've been playing around with reverberation chambers for about as long as I've been helping to write DO-160 for about 30 years. I have to confess that when I first got introduced, I was skeptical because I was a direct illumination anechoic chamber guy, and I had some big fancy antennas that I used for running high-level tests using the anechoic chamber method, the direct illumination method. And it didn't take long after I started using reverberation chambers to become a convert. And some of my colleagues, especially on the on Special Committee 135, the committee that writes DO-160, some of my colleagues there would say that I'm a bit of a fanatic as well. So I'll apologize ahead of time if I start to get evangelical about reverb chambers during this talk, but we do have a lot of reverb chambers within Element. I've got a list at the end of the presentation. But of course, we do have a lot of these semi-anechoic chambers, big 10-meter chambers, chambers like this designed for specifically for defense and aerospace. So we'll run the test however you want us to. We can do it any way you want us to. The other thing I'll say is that if anybody has questions throughout the talk, feel free, raise your hand, and I'd love to answer questions. Okay, so getting started here. So usually you get acknowledgments at the end. I put them in the beginning just to make sure everybody kind of knows where we're coming from here. First of all, Mike Crawford and Galen Kepke. I haven't met Galen Kepke, but back in the 90s, I met Mike Crawford. And he's also the inventor of what's called a Crawford cell, which we have here at our Tempe lab, the little Crawford cell, that little brown cubicle thing that's sitting on the floor in there. So really, it isn't really used for testing as much as it's used for things like calibrating field probes. But Mike Crawford invented that. But Mike Crawford and Galen Kepke, back in 1986, published NBS, which is what NIS used to be called, NBS Tech Note 1092, which was the definitive document that even today gets referenced by anybody who has any questions or wants to do research on reverberation chambers and how they work. It is, you know, like I said, 146 pages. It's exhaustive. It is a great thing. So if you want some reading, you want to know about reverb chambers, that still is one of the best references out there. I also want to give a shout out to Jeff Vail. He had this great presentation he put together about DO-160G, and it contained everything about DO-160G, EMI, and power input testing. But the section that was on section 20, the part of it that covered section 20, and especially the reverb chamber section, contained a lot of good stuff that I used as the starting point, as a building block for this presentation. So his work saved me a lot of work. So I want to give a shout out to Jeff. Jeff is still with the other element U.S. Space and Defense. But I also want to shout out to my best friend, Billy Martin, no longer with us, unfortunately. But Billy Martin worked for Boeing, Cessna. Before that, he was trained in radar by the U.S. Marine Corps. So he had a great background, a great foundation of nuts and bolts technical, especially with antenna theory. He was very, very good at that. And he really is the reason why reverberation chambers got into DO-160. Billy Martin made it happen. He made a lot of other things happen in the aerospace industry as well. But again, I could write a book about Billy, but he taught me more about reverb chambers than anybody else. Okay, so reverberation chambers are used for many types of EMC tests. So it's not just radiated susceptibility, all that. It's primarily what it's used for. DO-160 is probably the most frequent test. DO-160 RF radiated susceptibility in accordance with section 20.6 is probably the most frequent, but it's used for many others as well. You can run RF radiated emissions. Section 21 has a method for running radiated emissions. It's the best way to do a shielding effectiveness test, I believe. You can test all kinds of different things. We run a lot of tests for testing cables for shielding effectiveness. You can also test antenna performance. You can't get necessarily beam width, but you can get antenna efficiency, other parameters about the effectiveness of an antenna. These different standards, DO-160, of course, MIL-STD-461, DEFSTAN 59-411, that's the UK MOD standard. And there's an IEC standard out there that you can use for commercial equipment. Typically, that standard is usually specified for shielding effectiveness tests, but you can test a laptop computer for immunity testing using 4-21 if you wanted to. Very few people do. I think they're wrong, but that's me. And then that IEC, the EIA spec, I got up really early this morning, so forgive me if I stumble a little bit. That's for shielding effectiveness of cable assemblies. So just to put some history there, that EIA spec is an old one. So it's been around for a long time. And even back in the 80s and 90s, there were specifications out there, standards that said use reverb chambers for this type of test. Again, that's a shielding effectiveness test. So DO-160, again, DO-160 is probably, we run more reverb chamber tests in accordance with DO-160 than any other standard, by far, probably 20 to 1, almost 100 to 1. It's very popular in the chambers we have around element. That's what we use. And in DO-160D, the original version published in 97, that's when I started working on DO-160 in 97. The first version got into the document, the first version of reverb chamber testing. And again, it was pushed in by my good friend, Billy Martin. And it was a little primitive, but it was a whole lot better, in my opinion, than the direct illumination or anechoic chamber method that was in DO-160. Again, I won't go through all the details there, but I want to point out that it was the lowest usable frequency. In other words, there's a limit on how low a frequency you can use the chamber was based on volume. You didn't do the field uniformity calibration that we have to do today. Change number 1 to DO-160D published in 2000. And I was there for every all 10 of the working group meetings where we came up with the reverb method for DO-160 change number 1. And it looks very much like the modern version that's in DO-160 now. Again, you have to do this empty chamber calibration using E-field probes and antennas. So it's a detailed 9-position calibration process. DO-160E, no real change other than the standard deviation was we realized it was a little too tight. DO-160F added the option to do radiated emissions using a reverb chamber. And that was kind of a precursor to DO-160G, where we went back to the mode stirred method. So we went back in time, and now we're back doing mode stirring. That was published in 2010, like we originally had in 1997. 461, MIL standard 461, the other standard we use. Very rarely is the mode-tuned reverb chamber method used in MIL standard 461. It got put in there in 1999 when 461E was published. Got written by a guy named Mike Hatfield, who at the time ran the Naval Surface Warfare Center in Dahlgren. And Mike Hatfield also was very active, very involved in writing the change number 1 to DO-160D back in 2000. And he put his version in 461E in 1999, and it hasn't changed since. That's literally word for word the same, test everything for the last 27 years. No change since then. And I think Mike Hatfield has retired by now.
So it's the same in 461G right now?
461G, 461H, which was just released.
Okay.
Hasn't changed a bit. Exactly the same, literally exactly the same process. So, 2 different ways of running radiated susceptibility, RF radiated susceptibility. You can do it the wrong way in a semi-anechoic chamber, or you can do it the right way in a reverberation chamber. Again, I'm a little evangelical about that, but that's my opinion. My experience after 40 years of doing this is that the right way is in a reverb chamber. And as you can see in a reverb chamber, it's the tuner in the back, antennas, a receive antenna, a transmit antenna. We're doing calibration here. You can see the field probe there on the left. So I'll cover a little bit about the wrong way, just to highlight why the right way is better, why the reverberation chamber method is better. So for radiated susceptibility for DO-160, you've got a calibration ahead of time where you put a field sensor out in front of the antenna, crank up the power till you get the field that you want, record that power level, go to the next frequency, repeat, and you do that calibration on an open area of the bench, an empty bench. And then when you run the test, you use that same power level that you recorded and you play it back to run the test with the antenna pointed at the EUT. There are a lot of problems with that, and I've got a whole presentation where I talk about why this is a bad thing as compared to reverb chamber testing. I won't go into that, but just know that there's a lot of issues with that, I'd be happy to talk about that if you want me to. So there's a picture of a calibration. Field probe is the orange ball out in front there, and the antenna is aimed at it, empty bench. And then the test. Instead of the orange ball, we've got the test unit out in front of the antenna. So MIL standard 461, again, it hasn't changed from E through H. And again, the calibration for MIL standard 461, they don't do it. There's no calibration for 461, which is kind of annoying, but that's, again, I could talk a lot about why that's a problem, but I won't for right now. 461, you use any kind of linearly polarized antenna. Field sensor placement is, 30 centimeters above the ground plane up to 1 gigahertz, and then next to the EUT for frequencies above 1 gigahertz. Then they've got this statement about do not place sensors directly at corners or edges of the EUT or components. But where else are you going to put them if it's not at the edges of the EUT? Because you're supposed to place the field sensor near the EUT. That's another talk. I'll be happy to give that later. And then there's a little deal in 461F where you could use a receive antenna, only 461E through F. You could use a receive antenna to calibrate, which actually makes more sense because you put the receive antenna on the empty bench, and then you record the power level required, and then you play back that power when you run the test. Thank you. But almost nobody does it because you still have to use an E-field sensor for frequencies below 1 gigahertz. So it virtually never happens. And again, this is a picture of a setup for a MIL-STD 461 test. Antenna out in front, field sensor right by the unit. Again, I don't know how you place the sensor not on corners when you've got to place it right next to the unit, but I do as I'm told, They didn't ask me. The Tri-Service Working Group that writes MIL-STD 461, they're kind of this close-knit group of these old guys who've been running EMI testing at the military laboratories, right? They don't invite, the outsiders. They have a couple of consultants that they hire from industry who've been the same people who've been there for about 40 years now. And, I think they get paid actually to attend Tri-Surface Working Group. But anyway, those guys write the standard for their own purposes. And the guiding principle of MIL-STD 461 is we've always done it this way. Okay, so what is a reverb chamber? What is a reverb chamber? So a great example of a reverberation chamber that you can find in just about everybody's home, including this laboratory, is a microwave oven. A microwave oven is a reverberation chamber. Single frequency, operates at about 2.5 gigahertz, right? And the reason, instead of having a stirrer, although some microwave ovens actually do have a little bit of a stirrer involved, a piece of metal that spins around, but you typically rotate what you're cooking, right? So that's how you get the distribution of the heat on the thing that you're trying to heat up. So if you've ever noticed, there are no such thing as really big microwave ovens, right? And there's no such thing as really small microwave ovens, because a microwave oven has to be big enough so that it works good at 2.5 gigahertz. But if you make it too big, you need much more power to heat up the same amount of meat or whatever your water you're heating up. So there's always a very small range of the size of a microwave oven. Some industrial microwave ovens, and I'm talking the ones where they try and heat up material to seal it or something like that. They can be bigger, but they've got actual stirrers in them, right? And they've got much bigger magnetrons that produce much higher power levels than the typical, even commercial microwave oven that's used in a restaurant or whatever like that. So it's a resonant cavity, and it can be used for emissions and susceptibility. So the other thing I'll point out is that typically it's lined with, it's got to be all conductive material on the inside, and the more conductive the material, the better. Copper is better than aluminum. Aluminum is better than galvanized steel. You'll notice in the chamber here, we've got a lot of copper on the walls because it makes the chamber perform better. It's a higher Q. You got to have a tuner that moves around, and then you've got a transmit antenna and a receive antenna. You'll always have a transmit and a receive antenna inside the reverb chamber, whether you're when testing and calibrating. So this is one of our reverb chambers in Minneapolis. And again, highly reflective surface. You get a lot of standing waves. You launch the RF energy in, inject the energy, lots of standing waves. And it works the same with sound, by the way. If you put like a 1 kilohertz tone from a speaker in this chamber and you walk around in there, it'll be loud over here, it'll be softer over here, louder over here, because you have standing waves. You have the peaks, and you move those around when you rotate the tuner. So as you move the tuner around, it changes the boundary conditions in the resonant cavity. And so you move those peaks all around. So this right here, I love that. Jeff did this, and for that I'll be eternally grateful. That is a wonderful illustration. So you can see as you get constructive and destructive interference. So when you have the constructive interference, when the peaks align, then you get a high, you get a peak inside the chamber. The standing wave is high. And when they cancel, when you've got destructive interference, then the peaks drop off. So that's a beautiful thing. And that's, you get the low and the high. And this difference between the peak and the valley is typically referred to as a stirring ratio. Typically, the industry likes to see a 20 dB or a 10-to-1 stirring ratio. A good reverb chamber, especially one that's lined with copper like this one, will have an even better stirring ratio. And so you want to look for that. Yeah, that's a mark of the quality of the chamber, the performance of the chamber. So as it says here, when you get constructive interference, they sum. When you get destructive interference, they cancel. You get this peaks and valleys. So we put our test unit, our EUT, in there. And if we didn't turn the stirrer, we just have peaks that happen in one place and nulls that happen in another place. But we rotate the stirrer, rotate the tuner, either in steps, defined increments, 10 degrees, 30 degrees, something like that, or you stir it slowly, continuous rotation. And there's different, MIL-STD 461 is only tuned. You have to step it, discrete steps. DO-160G, DO-160H is a continuous rotation of the tuner. So this is, let's see if I can get it to run here. Come on, there we go. Click. So this is another chamber in Minneapolis. This is a medium-sized chamber. This one's smaller. It's designed to work above 400 megahertz, but same demonstration as we've got in here. You can see the tuner is rotating slowly, and you can see the fields bouncing around there. So this is, you've got to do a calibration of the chamber. And this is the whole beauty of why we use a reverberation chamber. Notice the three different lines are, as I was saying, galvanized steel is the bottom one, aluminum is the middle, and copper is the top. So you can get for 1 watt of input power. Now this is a chamber that's calibrated down to 80 megahertz. Okay, so it's a relatively large chamber. But with the treatment on the walls, the copper on the walls, 1 watt of input power, and you get over 100 volts per meter at 2 gigahertz. Now, that's with no loading, right? Typical test units load down the chamber, so you won't get, you might get 1 watt will give you 50 volts per meter because you've got loading in the chamber. But still, that's a lot of field for a fairly low power level, right? And amplifiers are expensive. All of us in the business, if you can get by with a smaller amplifier, you're way ahead. So when you do the calibration, though, you always have, for whatever power you need to achieve the field, you're getting a relationship between the power injected and the field produced. So if you put in 6 dB more power, you're always going to get 6 dB more field. And the ability to produce lots of field with less power is, you can see the benefit. And when we're doing these, this is test levels, category levels that are found in DO-160. So worst case is category L there on the right. This is pulsed, but that goes up to 7,200 volts per meter in the frequency range of 4 to 6 gigahertz. And so if you're going to do that with a direct illumination antenna, you'll need like 6 or 8 kilowatts. If you do it in a properly sized reverberation chamber that has copper lining on the walls, you can get by with 1 kilowatt. You can get by with a much more reasonable level of power amplifier. And the same is true for the CW levels as well. CW amplifiers are more expensive for the same power level than a pulsed amplifier. So the shape of the reverberation chamber is not critical. So it can be any height, length, ratio of height to width, length doesn't really matter. However, certain shapes perform better than others. And this chamber, it's hard to tell, but this chamber, the ceiling is sloped. It's not parallel to the floor. And that odd angle on that one surface improves the field uniformity. It's easier to get a better field uniformity if you have one of the surfaces or more of the surfaces that aren't parallel. And this is one of those things I built. I lost track. Seven reverb chambers, 8 reverb chambers. But anyway, over the years I figured that out, that sloped one, having a wall that isn't, or one of the surfaces that isn't parallel with the other, improves the field uniformity. You get better field uniformity for the same volume of chamber. And again, the interior surface treatment has an impact on performance. Copper is better than aluminum. Aluminum is better than galvanized steel. As a matter of fact, galvanized steel really doesn't work very good above about 18 gigahertz. The performance really starts to fall off. The galvanized steel, because of the conductivity being so much poorer than aluminum or copper, you actually end up, it starts to absorb. It starts to act like absorber at those really high frequencies, 18 to 40. Yes, sir?
What thickness of copper are you guys using in there?
The thinnest we can get by with. It literally has no impact on performance. You can use aluminum foil or copper foil. Yep, the skin depth at the frequencies we're talking about is anything works. Yep. So the volume of the chamber, the total interior volume is the biggest factor in the performance. Like I was saying with the microwave ovens, you can make them smaller, right? So you get more power density. You put 1,000 watts in and you put it in a smaller space, you get more watts per cubic centimeter, right? Which gives you higher field levels. But that means that your calibrated volume, the area that you have the required field uniformity, gets smaller. And the usable frequency, there's a point where when you get too small, you can't meet the standard deviation. You can't meet the field uniformity requirements. You have to have a certain size to meet the field uniformity requirements at a specific frequency. But you can't get any smaller than that. So the chamber volume determines the lowest usable frequency. This chamber here has been calibrated down and meets the standard deviation requirements of DO-160 down to 100 megahertz. And this is the calibration process. You've got 9 positions, 3 axis probes. So you're getting 27 different values at each frequency. It's a very complicated process. Brandon can tell you how long it takes. But we do this detailed field uniformity measurement to validate that we've got a uniform field within a certain standard deviation across the frequency range. And of course, when you do the test in the anechoic chamber, nobody cares. It is whatever it is. You got a field sensor in one location, and then you just run the test. Anyway, that's another talk. I brought that up. I've talked till I'm blue in the face on that other venues. So anyway, the calibration when you're doing with field sensors like this is always mode tuned, because the field sensors have to have time to respond, and you've got to record those values. Now in DO-160H, I got them to agree that we could use mode stirred for the field uniformity verification, but you do that with small passive antennas instead of E-field probes. So there's a procedure for doing field uniformity in DO-160H, assuming it survives. DO-160H hasn't been published yet. I don't know when it's going to be published, but we keep arguing. Section 20 is the one we keep arguing about. But assuming it survives and gets put into the document, there's a mode stirred field uniformity method included in that document using small passive antennas. And by the way, go ahead.
So would the older versions of DO-160, the way they calibrate, that would still be valid, even if DO-160H has the new method?
DO-160H has both, has essentially exactly the same as we've had for the last 25 years with the E-field probes, the 9 positions with the E-field probes. But we added this option for the mode stirred method as well. It's an optional method.
Great.
Now, for your lab, any of the element labs, we do both because there's advantages to a calibration using the mode stirred method. Matter of fact, I've done this, and the field uniformity is much better actually when you do mode stirred. It's much better than the mode tuned with the E-field probes. So that's an option that's coming in DO-160H whenever that gets published. Hopefully, I don't know. I'm gonna say sometime next year. The committee, the people running the committee, really want it to happen this year, but I don't think it's going to happen. There's just too many open issues. So again, chamber calibration, field uniformity verification. You've got to have the receive antenna. You've got to have the transmit antenna. You use the same receive antenna and transmit antenna for the calibration as you do for the test. You're going to always have those 2 antennas in the chamber. And you want them positioned so that they're not aiming right at the test unit. Typically, you're aiming them at the corners, you're aiming them at the tuner, something like that. And they have to be, it works better if they're a little skewed. You notice how this one is a little off angle in all different directions. So you've got to, when you do the calibration, the field uniformity verification and the calibration, you've got to have the antennas in there and you've got to have the probes in there. And you're continuously moving the antenna around, moving the probe from one location to the other, all 9 different locations. So you end up with lots and lots of data, lots and lots of calibration data when you're in this process, as opposed to the anechoic chamber method where you end up with 1. Anyway, so this is a setup in one of our chambers. This is the chamber in Melbourne. I guess you can't, this is the receive antenna and the probe in 2 different locations. This is a smaller chamber designed to operate above 400 megahertz only. It's got a vertical tuner as opposed to a horizontal tuner. Horizontal works, vertical works. I personally prefer the horizontal orientation of the tuner because you end up with more usable space in the chamber if you put the tuner up close to the ceiling, but either one works. And there's a transmit antenna in there that you can't see. It's off the page somewhere. And I think, yeah, this is in here, yeah. So this is another. So again, with no EUT installed, no bench, no EUT, you've got the field sensor over there in the corner. You got the transmit antenna is this. This funny looking thing over here is actually an antenna used to inject energy into the chamber. Use it, what, 100 to 400 probably? Yeah. And then a receive antenna over here. And you step through. Normally you use 1 watt of power, makes the math easy to do a 1 watt. And then you just move that probe around and move that antenna around through all the different positions. And in DO-160, the currently available standard, DO-160H is different, of course, like I said, but all the standards out there, you move the tuner incrementally over a 360-degree rotation. You stop at each position long enough to make the measurements with the probe and the antennas. So in here, did you do what, 10 degrees, 30 degrees?
10 degrees.
10 degrees, yeah. So and you You use the same number of steps during the test as you do during the calibration. So you got to use 10-degree steps during testing since you calibrated with 10-degree steps. And this process is repeated at every frequency for each of the 9 field probe locations. And you've got to do it at 50 or 100 frequencies per decade, from 100 megahertz up to 18 gigahertz. So long time. A lot of positions, a lot of frequencies, long time. Different antennas.
How often do you have to do it?
So the standard says that when you first build the chamber, you have to verify the field uniformity. You have to make sure that the treatment on the wall, the material on the walls, the size, the shape of the chamber, you get the field uniformity requirement. And then if you make any major modification, like say you go from galvanized steel on your walls to copper on your walls, or you go from a vertical tuner to a horizontal tuner, something like that, you have to redo the chamber calibration. This is the standard deviation for all 27 values. So it's basically a 2-part process. You take all 27 values, so you have 9 locations, 3 axes on each probe, and you take that data, all 27 values, and you determine the standard deviation for all those points at each frequency. And this is a plot of this chamber, actually. And you can see that. So we got the sloped down from 6 dB down to 3 dB. I tried to draw a line here, but I'm not very good. I used to be able to use Excel, but I'm used to the 97 version of Excel. You do graphs real easy, but you can't use that anymore. So this is the 2025 version of Excel, and I couldn't figure out how to make a line on the stupid graph. Anyway, so I put big dots there that would make it easy to see. So 6 down to 3 at 400 megahertz, and then straight across. And you can see that we got a little bit close right at 400, but we're still meeting the requirement. We're meeting the standard deviation for this chamber down to 100 megahertz, from 100 megahertz to 18 gigahertz. And for most of the frequency range up here, I mean, it's under 2 for almost all of it, except for this one outlier here. So this is a really good field uniformity. And that's, across the whole volume of the chamber. And we got less than 2 dB. And go ahead. Yes, sir.
Good question. Going back to sliders, you don't have to go back. I noticed that your tripods were metallic tripods.
Yeah.
Okay, instead of phenolic. How would you answer a question about the impact that would have in making these measurements?
It's another reflective surface. Doesn't really matter. We try to actually avoid the non-conductive tripods a little bit, because certain, and I don't know, I can't find a rhyme or reason. I'm not exactly sure why this is, but there are certain tripods out there from certain manufacturers that will just load down a reverb chamber like crazy. I don't know why. We always try to use metal antenna supports whenever possible inside the reverb chamber, because it's a reflective surface. You don't have to worry about loading. But it might have a small impact, but you'll find that out when it's nothing compared to the change that you get, the impact that you get from putting a test unit in there. The test unit provides a lot of loading, and you verify that when you have to do a loaded calibration to make sure of how much power you actually need. But it's a very minuscule contribution.
So if I understood you correctly, are you saying that non-metallic tripod would have more loading
than a metal tripod?
Yeah, right. Okay.
Yeah. We try, and it's unpredictable. That's the problem with metal tripods. Metal antenna supports are very predictable. They're just going to reflect. But the non-metallic, some materials it's weird. Some materials will absorb a lot of RF energy. We've had antenna, I've seen antenna tripods where we get melting, arcing from antennas because for some, I don't know how who would make a tripod that's, out of conductive material designed to have an antenna. It's supposed to be a non-conductive. I mean, I understand you don't want, you can avoid how you don't want an antenna touching a metal tripod. But, this tripod that's supposed to be non-conductive, all of a sudden, just because there's an antenna next to it, it starts melting. It's crazy. Anyway, so again, all 27 positions, the standard deviation comes in nicely. This gets a little busy, but you also have to evaluate each axis. So you got the 27 positions have to meet the requirement, but each axis has to be individually evaluated. And you're only allowed, see how we've got a couple of frequencies that go above the limit down here at the low end? So you're allowed to have, in any particular axis, you're allowed to have 2 frequencies per octave that fall out of the standard deviation requirement. So it's really hard to get every single axis in. It's next to impossible. It's not impossible, but it's hard to do. So that's why there's an allowance for, if you have an outlier like that one down there around 140 megahertz or whatever that is, that's okay because the full standard deviation is in. The full standard deviation of all 27 has to meet, and all but 1 or 2 per octave has to meet on all the axes, each individual axis. Again, a very complicated process. A whole lot. And then you compare that to the anechoic chamber method. But again, that's another talk. So you determine the lowest usable frequency for DO-160 by making the measurement. It's performance-based. DO-160, you measure what your standard deviation is, and if it meets down to 200 megahertz or 400 megahertz or 100 megahertz or 1 gigahertz, whatever, that's your lowest usable frequency for your chamber. Performance-based, you make a measurement, you determine it. MIL standard 461, again, the reverb chamber method was written by this guy named Mike Hatfield. He talked to me about when he put the reverb chamber method into 461 for the option for RS-103 testing. He said, yeah, I had to dumb it down for all the military EMI labs out there. He said they wouldn't listen to, they weren't going to have any of that calibration, standard deviation, all that. He said, you just make sure that it's big enough. And then, like everything in the military does, double that, add 6 dB just to be safe. And we're going to make sure that the chamber is big enough that it's definitely going to support enough modes to have good field uniformity. And even then, they won't let you use a reverb chamber below 200 megahertz. So you have to, so RS-103, right, starts at 2 megahertz for the most part, right? So you got 2 megahertz to 200 megahertz that you have to do in the anechoic chamber, semi-anechoic chamber. So why would you then, when you're already set up, you've already got the amplifiers, and you already got the antenna, and you've already got the semi-anechoic chamber, why would you say, okay, let's go to the reverb chamber for above 200 megahertz? Nobody does. Except we have certain customers that do RS-103 that got so frustrated, having ready to stroke out because the repeatability of the test results above 1 gigahertz in the 1 to 4 gigahertz range, they had terrible repeatability. And they spent weeks trying to figure out, well, what is the actual test level? And they kept, because you have to have the field sensor right next to the test unit when you run the test. Well, you're getting reflections, 1 to 2 gigahertz wavelengths, like this, quarter wavelength. You're getting reflections off the test unit. You're getting reflections off the bench. Move the field sensor a centimeter, and you get twice as much field or half as much field. And they were just like, this is crazy. Why do we do it? And I said, well, you got to talk to the Tri-Service Working Group. They don't listen to me. So finally they said, can we do this in the reverb chamber? Oh, sure, yeah. They ran the test in the reverb chamber. Repeatability over, it's like clockwork. They could repeat the failures. They could repeat the field levels over and over again. And since then, since that incident, they won't do RS-103 in anything but the reverb chamber. Well, above 200 megahertz. So there's a couple of converts out there, you know, and maybe we'll get more. I don't know. But yeah, RS-103 is it's a lousy test method. But again, that's another topic. So there's our reverberation chamber with the bench installed. So now we're ready to test. Our calibration's done. We had the bench out during the calibration process, the field uniformity verification. Bench is installed now. We've got our tuner, we've got our transmit antenna, with the receive antenna is hanging off somewhere else outside the frame there. So you have to do a loaded chamber calibration. Again, we're talking about DO-160, right? Because that's the primary, that's the standard everybody uses reverb chambers for, right? If you're going to do a reverb chamber test, odds are 90% of the time we're doing it for DO-160. So you've got to, with the EUT installed and the cabling all laid out like it's supposed to be in the chamber, you're going to do what's called a loaded chamber calibration. So for the stirred method, you're going to have rotate the tuner continuously, and you have that receive antenna, and you measure how much power you're picking up with the receive antenna that's in the chamber, and then you plug that data, that measured power level from the antenna, directly into a formula. You calculate that says, I put in 1 watt, and I've got 50 volts per meter for that 1 watt that I put in with the EUT, with the system set up in the chamber. And then you use that to determine what your power level what power level you need for the test. D160D through F, it's more complicated because it goes back to the field level measurements that you made with the E-field probe. And there's a complicated formula to determine what's called E total for how much power is required to achieve a certain field. But you verify how much loading you've got based on the loaded chamber calibration. So again, you're stepping through, 36 positions or however many positions of the tuner, and you're measuring how much your received power is. But what you're doing with that measurement of received power, you're not plugging that directly into a formula. You're saying, okay, the received power I had during the calibration when the chamber was empty was this. My received power I have now that I have my test system in the chamber is this. And so I correct that E-field that was determined by the E-field probes by that amount. So yes. See, I had to go back. I had to go through these pictures. I didn't want to pick pictures where it was easy to tell what was in the chamber, right? Because that would be like violation of privacy, right? So this was a picture where you can't really see what it is very well, but you also, it's kind of dark and dismal. I don't know. But anyway, this is the loaded chamber calibration. The receive antenna is there, and the EUT is in there. Again, the transmit antenna is off over here out of the frame. So loaded chamber calibration, you plug the results into this formula. So bottom line is, when you did the calibration, you come up with that you can get 100 volts per meter for 1 watt of forward power, which is not unusual. Smaller chambers, some of the smaller chambers that we have will do that. If your actual test level is 2,000, which is 26 dB more, that means you just need 26 dB more power. So you did the calibration with 1 watt, you got 100 volts per meter. Your test level is 2,000 volts per meter. So you put in 26 dB more, 400 watts when you run the test at that frequency. You do that for every test frequency you make this calculation. And generally the software does it for you, so that makes it easier. So that's another another loaded chamber calibration setup. I just thought that was a cool picture because we've got, this is a hydraulic unit that in our Minneapolis lab where we had to tent it over with the poly there to make sure that if it started spraying oil, it didn't go everywhere. We do a lot of hydraulic stuff in the Minneapolis lab. So for 461, again, hasn't changed since E, published in 1999. You can either use the E-field probe, an E-field probe, to make the measurement, or you can use a receive antenna to make the measurement. In either case, you're putting the probe in there with the test unit in the chamber, and you're stepping the tuner through the number of steps that MIL Standard 461 says you have to take, and you're either recording received power from the antenna, or you're reading the E-field probe. In either case, you come out with this value that says for 1 watt of input power, here's how many volts per meter I'm seeing inside the chamber. And you do that same correction for adjusting the amount of power to apply to the antenna for whatever test level you need. Again, it's this formula that's in 461 for the receive antenna. That's different than what's in DO-160. Even though the guy who wrote 460 with the RS-103, the reverb method, helped write DO-160. He didn't agree with the formula that ended up in DO-160. That's another talk as well. So again, this is an RS-103 reverb chamber test setup. Field probe is in there. And you don't see the transmit and receive antenna, but this is, you don't have to set it. The one benefit of the field probe method for reverb chamber, you don't have to put it right next to the EUT. You just have to put it somewhere that'll be in the uniform volume of the chamber. So in DO-160, the mode stirred method, this is another picture of our, this is an all aluminum chamber. Usable down to starts at 1 gigahertz. Gets really high levels in this chamber because it's so small. But anyway, you've got, when you're doing the test mode stirred for DO-160G and in H, theoretically, you're continuously rotating the tuner, and the stirring speed is defined in the standard, 4 RPM below 1 gigahertz, 2 RPM above 1 gigahertz. And you apply that calculated P target, how much power you need to produce the field that you're trying to achieve inside the chamber. Again, your receive antenna is always in there. That's another thing is that if you record the values that you get on the receive antenna during the test, then you know for sure that you achieved the field. Whereas when you're running the test in the anechoic chamber, you're just assuming that you're still producing the same field that you got during calibration. Reverb chamber, you know you do because you're measuring it. The receive antenna's in there the whole time. Tuner speed for when you're doing mode stirred. If you're doing something that's gated, which a lot of times, a lot of these DO-160 tests, you have like a 1 hertz gating. It's on and off at a 1 hertz rate. Then the guidance is that you should slow down the tuner accordingly. Typically cut the speed in half when you're doing that gating. So mode tuning, whether you're doing 461 or DO-160, older versions of DO-160, again, you're applying that calculated power level to the antenna, what you need to produce your field, and you're stepping the tuner through the same number of steps that you use during the calibration, during the loaded chamber calibration. And then we've got field uniformity verified here at 10-degree steps, right? So you've got to take at least the same number of steps that you took during the field uniformity validation. You can take more, but you take the same number of steps during the loaded chamber as during the test, okay? So you can take 72 steps instead of 36, but you have to do that for both the loaded measurement and the test. And then you have to dwell at each tuner position and each frequency for however is specified in the standard. DO-160, the minimum is 1 second. You might do longer. RS-103 is 3 seconds. So at each tuner step and at each frequency, you have to apply the correct power for that frequency to produce the field that you need based on the loaded calibration. And then you scan over the frequency range based on the step size. 461 uses smaller steps than DO-160. So you can either step the tuner, scan through the frequency range of the antenna that you're using, and then step the tuner again and scan through the frequency range. Or you can sit at one frequency and step the tuner through the full 360 degrees. Either way works. It's just a matrix you have to fill in. At each step, you got to do these frequencies. So you either do one frequency and step, 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 or you do one step and frequency, frequency, frequency. Either way, you got to fill in the matrix. Either way is valid. And there's a picture of one of our chambers. Like I said, I tried to include pictures because I thought it would make it more interesting, but it's hard to see. There's a transmit antenna back there. There's a receive antenna up over there. The test unit is this thing that's held down by C-clamps to the, there's a ground plate in there. And there's the tuner in the background. This is another copper line chamber. This one is calibrated to start at 400 megahertz. You can also do radiated emissions. Section 21 of DO-160 includes a method for doing radiated emissions. And you won't be surprised to hear that I think this is the right way to do it, the right way to do radiated emissions as well. And the Section 21 radiated emissions using the reverb method is written so that you don't have to change anything with your setup. And if you've run the loaded calibration for Section 20.6, you have all the data you need to plug in for providing a correction factor for your emissions measurements for Section 21 using the reverb chamber. You have you still have the antenna. Again, antennas stay in the room. It's a little bit of a math problem. You've got to do 200 sweeps for a full rotation. You've got sweep speeds and bandwidths, and it gets to be a little bit of a math problem to figure out the number of sweeps to do over a given frequency range to make sure that you get it right. But thanks to Excel, it makes it easy. Excel makes that all that easy. And then you gather the data and you compare it to the specified limit. There's no difference in the limits whether you're doing anechoic chamber or reverb chamber. The emissions limits are the same. And for DO-160F, because we added the reverb chamber method for emissions, that's when they changed the lower frequency for radiated emissions to 100 megahertz. Used to go down to 30 megahertz. And in older versions, it went down to 2 megahertz. But in DO-160F and beyond, the radiated emissions limits start at 100 megahertz. And that was specifically done so that you can use a reverb chamber.
So for MIL standard, starting at 10K, I assume you would use reverb chamber.
MIL standard 461 does not allow RE102 to be performed using a reverb chamber. No option at all. That's another reason why there's not a lot of reverb chamber tests done for RS-103. It's because you've got to set it up in the reverb in an anechoic chamber to do RE102. You're already there. And then you've got to use the anechoic chamber for 2 megahertz to 200 megahertz. Why would you switch a 200 to go, unless you almost had a stroke like that one customer of mine who was trying to do that RS-103 test in the 1 to 4 gigahertz range and couldn't get repeatable results. So a brief summary here. Pros and cons. The reverb chambers are widely accepted, a lot of different industries, a lot of different standards. For emissions, as it says there, you'll always find the emissions and you'll always get very repeatable results in the reverb chamber. Because if you've got an emission that's coming out over here at this odd angle, you're always going to find it. You aren't going to be subjected to small changes in spacing between the cables affecting the radiated emissions measurements. and you aren't going to have to worry about, well, precise positioning of the EUT because you've got a real narrow beam width of the emission coming out of the EUT over here that one day you get it and one day you don't. Reverb chamber, it's always going to be repeatable. You're always going to get the same results. And the same. Go ahead.
I think that's very nice for testing measurement, but for troubleshooting, that's up there. We don't, when you're in an anechoic chamber, you can rotate the unit or the antenna and say, it's coming from right here.
Yes, you are correct. You are correct. So if you want to determine which seam is leaking in the reverberation chamber, it is a little bit more complicated. I will agree with that completely. However, it is also much more repeatable. I started out my career working third shift on an open area test site out in the middle of nowhere in Minnesota, where I had to worry about bears coming out of the woods when I locked up and went home, second shift or third shift. And troubleshooting, and yes, you're right, the emissions measurements were, you could find out which angle they were coming from and get a little bit better idea on where that emission was coming from. But also, it was really hard to get a repeatable measurement. And it's even worse, okay, when you're doing this test for DO-160 or MIL-STD-461 in a anechoic chamber on a copper bench where the thing is bolted down to the bench. You really can't rotate it very much, and again, small changes in the position of the antenna, small changes in the layout of the cable can really affect your emissions measurements. The thing with a reverb chamber is you can always go in, and this is what we do. So you get an emissions problem in the reverb chamber. You're right, it's coming from somewhere on the box. Well, that's when you break out the sniffer. You start looking on seams, and you start measuring. Measuring cables, right? And then if you find something, put that copper tape on that seam, see if it gets better. But your troubleshooting is always very, very repeatable. You'll know for sure if you got it. Yeah. But I agree with you. There's some limitations, especially with emissions, where it's getting in.
So would the spatial distribution of your results help you point towards the source of that noise?
It could, yeah, it could, yeah.
Geometry.
Sure, yeah.
If it's strong enough.
Right. Yeah, exactly right, yeah. The other pro of reverb chambers, like I was talking about, is you can get very high power levels with very high field strengths with relatively low power levels. And again, I can't emphasize enough, the highly repeatable results, whether it's emissions or susceptibility. And, in Minneapolis, we have 4 different reverberation chambers, different sizes and shapes. One of them starts working at 1 gigahertz. So if you got a failure, we've tried this, we got a failure at, say, 2 gigahertz. We can repeat that failure within very tight tolerances in all 4 of the chambers, and they're all different sizes and shapes. And that's next to impossible in the anechoic chamber. That's really, really hard to do in the anechoic chamber method. Cons, a full test is achieved over many tuner positions. So if you've got a simple box and you're only going to test, one antenna location right out in front of the box, it's going to take you longer to do it at a reverb chamber as compared to the anechoic chamber. It'll take longer. I think it's a better test than the reverb chamber, but still, you can run the test according to DO-160. Anechoic is faster. If you've got a single box you're only going to test one side of it. Now you're probably dumb to test only one side, or maybe you're not. I don't know because I guess it costs less money. But the other thing is that your lowest usable frequency is limited. So you've got to have a fairly large chamber to get a lowest usable frequency down to 100 megahertz. You're typically going to have a chamber that same size for anechoic. Your anechoic chamber is going to be that big as well, but that's a trade-off of lowest usable frequency based on size. And again, RS-103, you can't use it below 200 megahertz. If you've got a lot of loading, if you're putting in a system that loads down the chamber a lot, then you're going to need a lot more power. And that's the one thing about a reverb chamber that can be a little annoying is you don't know what your loading is going to be until you start. You got to measure it to know. You know, I've been doing reverb chamber tests for about 30 years, and I've gotten to the point where I can pretty much give a good estimation of what the loading will be for a given system, but I still get fooled once in a while where I had a system that I didn't think was going to load the chamber at all, but they had these cables attached that they had some kind of RF absorbing material wrapping the cable. I don't know what it was, but it was like loaded the chamber like crazy. Just these cables, the jackets on these power cables on the system. Anyway, so you just don't know what the loading is until you actually measure it. And the other thing is what you're testing has to fit within the calibrated volume. So if you're going to test a large system, large EUTs, you need a larger chamber. Larger chambers mean you need more power. So, summary and a little marketing. Reverb chamber has been around for a long time, and I think they're a superior alternative. Element has lots of reverb chambers installed in the U.S., and there's 2 in the UK, 10 scattered around the U.S., various different sizes. In our lab in the UK in Wimborne, they have 2. And we've got more reverb chambers planned to be installed over the next few years. Talking about maybe taking this one over here and converting it into a reverb chamber. So this is look to have more of these as time goes on. We're also installing anechoic chambers too, so we're not just putting in reverb chambers. We're expanding in a lot of different ways because MIL-STD 461 still got to have that anechoic chamber. It's hard to get by without it. And thank you. Yes, sir.
Question, wasn't going to let you get off that easy. Can you give some gut instinct for the how much more power? And where I'm coming from is if you ever build a chamber, you have to justify, the power of your amplifiers and everything. The difference between galvanized metal and aluminum, and then aluminum and copper plating or copper chamber walls is like some kind of gut feel for how much more power you're going to need in one or the other for a given volume.
Easy, a safe assumption. Copper, as opposed to galvanized steel, you're going to need twice the power for galvanized steel. So if you think about how much a copper costs, even though copper costs a lot these days, right? A 400 watt amplifier costs a whole lot more than a 200 watt amplifier, or a 2 kilowatt amplifier costs a whole lot more than a 1 kilowatt amplifier. So it's definitely worth it.
How about the difference between aluminum and copper?
It isn't quite as good. Aluminum is still better, and aluminum's cheaper.
Yeah.
So yeah, I would, if I was building a new chamber, and I am building a new chamber soon, but I would not use galvanized steel on the inside. It's just, I mean, this chamber over here that we're talking about retrofitting has galvanized steel already on it, but it's easy to pull up the clamps and just put a 4x8 sheet of copper under there, clamp it back down.
What do you get feel like, hey, 20% more power, 50% more power?
I would say probably difference between aluminum and galvanized steel is probably 50% more power. Yeah, that's a safe number. In reality, you're probably going to find that the empty chamber is actually more like 3 dB and 6 dB for aluminum and copper. But the thing with a high Q chamber, with copper, is the effective loading from the EUT shows up more dramatically.
With the aluminum.
with aluminum or copper as compared to galvanized steel.
Okay.
So the same EUT that provides the same loading, it's going to show up more because you start with a high Q in the copper chamber, and so any little bit of loading is going to really knock that Q down really fast. Whereas a galvanized steel chamber, the Q isn't very high, so the added loading from the EUT doesn't have as much of a dramatic effect. So in the end, again, it's still well worth it, but I think a safe number, not looking at it from an empty chamber, but a loaded chamber, a safe number for a loaded chamber is probably about twice the power, or half the power for copper, and probably 75% the power for aluminum. Let's put it that way. So, and it's, again, I say it's worth it. Amplifiers are expensive.
So in the future, are you going with copper?
Always, yeah. Yep. Yes, sir.
So you mentioned that the largest dimension in the chamber dictates the lowest usable frequency, and the volume dictates the most efficiency frequency.
Well, the total volume dictates the lowest usable frequency, for the most part. I mean, if it looks like it's really narrow and really big, it's still not going to work. You still need some minimum dimensions, but generally it's the volume, and the shape has some impact on the performance as well.
So is there any formulas that you can use when you're designing a reverb chamber to make it more efficient in the higher frequency portions or the higher levels of the DO-160?
Well, an easy rule of thumb is to take that formula that's in MIL-STD 461, and it'll tell you what your lowest usable frequency is. Plug it into that formula. That formula takes into account is just ABC, length, width, and height, and you plug it into the formula, and it'll tell you how many modes you've got and what your lowest usable frequency is. And it's a very conservative estimate. That estimate is very conservative. Yeah. But smaller chambers, give you more power, more field for the same power, but they also raise your lowest usable frequency. That one chamber that was all aluminum I had the picture of, that's about this long. It's like 6-7 feet long. They call it the coffin. Anyway, but it's about that deep, and it meets the field uniformity requirements, that 3 dB standard deviation at 1 gigahertz. But for the same power, we can get in that chamber compared to our biggest chamber, we can get literally 10 times the field, because the volume is so much lower. It's pretty much a 1-to-1 effect. You reduce the volume by a factor of 4, you increase the field by a factor of 4 for the same input power. It's a square law. It's not a halving or doubling. I learned that the hard way one time. Thought I could reduce the volume by 50% or something like that, and I'd get a whole lot more field. I got a little more field, but not much. You got it literally. It's got to be one fourth the volume to get twice the field.
Would you just add a sliding wall in there to?
I have designs. I have scribblings on how to do that, and that might be my next chamber. It's not a sliding wall, but a ceiling that goes up and down. But anyway, yeah, you're exactly right. You could. But the problem is you got to have a way to seal it, because you don't want RF energy leaking around that. You've got to have a good seal around the edge. You got lots of figure stuff. Exactly, lots of figure stuff. Yeah. Yes, sir.
You talked a lot about the military standards, and that's very interesting.
Mm-hmm.
But we're actually, I think maybe the exception here, we're commercial FCC,
Yeah.
Part 15. What does the FCC think about this?
Last time I did any investigation, the FCC would not accept it. But we have worked with people trying to solve emissions problems to comply with FCC and troubleshooting in the reverb chamber. Just exactly like that. Try this, and it's a quick change, hold stirred,
Particularly for immunity, and it seems like the perfect thing for immunity.
Oh, I agree, absolutely. Yes, 100%. There's very few out there that do. I mean, but I think it is perfect for immunity, yeah.
Well, immunity for FCC, the way it's usually done, I call it the paint drying test, because it just takes forever.
Oh, yeah.
Moving everything.
Yeah.
This must take, does it take minutes? Because you're basically covering every direction every time.
Well, it's based on, so if you're trying to do low field levels, like what you do for CE marking, right? 10 volts per meter, let's say. You can use a really big chamber, right? That will give you really good field uniformity with a small number of tuner steps, right? So you can run through that frequency range really fast with a small number of tuner steps if you've got a big chamber, because you still can do it with less than 100 watts. You can do it with less power in the reverb chamber than you could in your anechoic chamber at 3 meters, 3 meters away. So yeah, I don't know why more people don't do it, but I think what the problem, of course, is it's new. It's not, it's different, and a lot of people just don't understand it, really. I mean, that's my purpose of my talk, is to educate everybody and convert you all over to the reverb chamber way of testing. So.
Well, thank you, everybody. Thank you, Eric.
Pleasure. Thank you for having me. Thank you. Thank you that nobody started the store. Didn't have to throw any cookies at anybody.
Brandon, I know, has a demo. If you guys haven't seen it already, sort of shows the same fluorescent light trick that Eric showed in the video. Feel free to hang out. There's more cookies. If anybody else wants tours, our cards are over here. If you have questions later on, feel free to get in touch with us. Take it back before you go. Some goodies, and thank you.
Really good swag. Thank you all.